Hello guys, welcome back to another video discussion in strength of materials, and in this video we will learn about beam. So in my past videos we talk about actually loaded structure, but when we say actually loaded structures, we are focusing on the structure that are subjected to axial force, and this axial force is acting normal or perpendicular to the cross-sectional area of that structure itself. Now, our beam has a different type of behavior or loading. Now, beam is subjected to different type of loads, and this load is acting perpendicular or normal to the longitudinal axis of the structure itself. Now, like for this example, we have this beam, and beam is a horizontal structure and are usually described by the manner in which they are supported. Like for example, this type of beam here, we name it a simple beam or a simply supported beam since it has pinned support in the other end and it has ruler support at the other end. Okay? Now this one is we have a cantilever beam. Now in a cantilever beam, when we have only one end that is being supported, and the support is in fixed support. Okay, like for example this one that is in fixed support. Now for overhang beam, we have a free end. Okay, the support here is in free end. We don't have support at this point here, but we have two supports in within the beam. Okay, just like with this one, it's an example of overhang beam. Now our beam, just like what I said, is being subjected to a transverse load. We have this one. This is a uniformly distributed load. We could also have a concentrated load. Now our concentrated load here could be acting vertically, or we could have a concentrated load that is inclined at a specific angle. Okay, and we'd also have a linearly varying load such as a trapezoidal load or a triangular load. And we have also a external couple. This one is a couple or a moment, no, that is also acting along the beam. Now, since we have supports here, we have pinned support, ruler support. We also have the fixed support. So how do you see these supports in real life? Now, for the hinge support, these are commonly bolted or welded or riveted connections, such as this one when we want to join beam and column structure. Now in hinge support, we are restricting our structure to move horizontally and vertically. Hence we have two reactions in our hinge support. That is, we have the horizontal reactions and we have vertical reactions. Now for ruler support, in this case, we are allowing our structure to move horizontally, but we are restricting it to move vertically. So therefore, it has only one reaction, and that is vertical reaction. So most commonly, roller support can be found in bridges, since we all know that bridges are exposed to heat, to high temperature, and that would cause thermal expansion. We should allow our structure to move horizontally so that we could avoid crackings in the joint. So we allow expansion of our beam. And then for the fixed support, we have three reactions. This is commonly used for concrete structure. That is when we connect column and beam concrete structure. We have horizontal reaction, vertical reaction, and we have also moment reactions, no, in the end support. Again, we have three different type of loads in our beam. We have concentrated load, and concentrated load is in terms of kilonewton, or it could be in terms of kips or kilopound, okay, or it could be in terms of pound, okay, or it could be in kilogram. So this same unit with axial load. So now we have uniformly distributed load. Our unit of uniformly distributed load is in terms of kilonewton per meter. Okay. Then we have kips per foot. Now for linearly varying load, we have changing load, and it changes linearly. Like for example, if we have trapezoidal load, we have triangular load, so the magnitude of our load there is changing across its length or across its specific range, is in terms of kilonewton meter, or we could also have kips foot for English unit. Okay, so these are some type of load. And also, as for addition lang, we have also couple, okay, or moment, external moment, and this is in terms of kilonewton meter, of course. Okay, since our being is being subjected to external load such as this one, we have concentrated load and we have uniformly distributed load. Okay, and due to this load, our beam experiences stresses on its cross section. Okay, and the value of these stresses must be determined so that as an engineer we can look, or we can have a proper design for this beam, and we can look for an appropriate dimension that is capable of resisting these stresses. Okay, now these stresses that we want to determine are caused by what we call internal shear and internal moment. Now, when we say internal shear, that is the force acting parallel to the cross section, and the moment here that is the one which causes bending in our beam. Okay, so if we're trying to draw the bending or the deflection of this beam, we would have most probably like this one. Okay, so this is an exaggerated drawing. Now, this is purely caused by our moment, okay, or by bending moment. Now, our moment here varies, or our shear and moment here varies along the beam, okay, or along the length of the beam. So therefore, we have different value of shear and moment at this point from the shear and moment of this point. So we have different shear and moment in every segment or in every portion in our beam. So our goal here in this lesson is to determine the internal shear and the internal moment in our beam. Okay? Now we have different method in determining internal forces or internal reactions. We have what we could use a shear moment equation, or we could also use shear moment diagram. But before we proceed to determining the internal shear and internal moment in our beam, we need to familiarize ourselves first with the different sign convention. Now, if we have external loads, which is acting like this one, if we have our couple that is rotating in clockwise direction, that external load, therefore, it is considered as positive. But when it is rotating counterclockwise, that is considered negative. Now, for loads that is acting downward, that is positive. Now, for loads that is acting upward, that is considered as negative load. Now, for internal shear force, if we have our shear force on the right face of our beam is acting downward, and on the left side of our beam that is acting upward, then these are considered as positive. Now, for our shear force on the right face of our beam is acting upward, and the left face shear force acting downward, then these are considered as negative. Now, for internal bending moment, if our bending moment like this one creates a upward curvature, or let's say that it's a smiling face or a smiley curve, then this is considered as positive moment, like this one, smiling. Now, if our moment creates a downward curvatured curve like this one, or a frowning face, then that is considered as negative. Okay, this is a negative bending, again, because this is frowning, and this one is a positive bending since this is smiling, or a smiling face. Okay, so these are some of the sign convention that we need to familiarize, and this will be helpful, no, in dealing with different problems pertaining to beam structure. Now, since our goal here is to determine internal shear and internal moment in our beam, so we could actually use two approach. So we have the first one is by using shear equation and moment equation, and the second one is by area method. But in this video, we will be focusing on the shear and moment equation, the conventional way in creating or in determining shear and moment. Now, using these equations, we will create shear and moment diagram. Now, basically, what is shear and moment diagram? Now, shear and moment diagram, it is the graphical representation of the internal shears and internal moments along our beam, so that we could internalize directly, or we could determine directly the shear and the internal moment at any specific point in our beam. So that's the use of shear and moment diagram. In order to create or formulate a shear and moment diagram, we need to first understand the relationship between shear and moment. Okay? Now, if we have positive shear, like this one, now we can say that a shear is positive when it is being plotted above our reference line, this one. Now, if our shear here is in zero order, or that is just horizontal, so our moment diagram is in linear, or is in first order with a constant slope. So like this one. So it is resembles as an upward ramp. Okay, so it is in the first order equation. Now, if we have our shear diagram that is in first order, or that is in linear, therefore our moment diagram should be in the second order, or that it should be in quadratic equation. Okay, now the curvature of our moment diagram in this case is upward. So we could say that if our shear diagram is increasing, then we have a smiley face moment diagram. Okay, a smiley moment diagram, like this one. Now, if our linear diagram or shear diagram is in linear and is decreasing, therefore our moment diagram is in frowning face and is in the second order, or in quadratic equation. Okay, so like this one, it is frowning. So again, just a quick review. If we have zero shear, zero order shear, we have first order moment diagram. If we have shear that is in the first order and it is increasing, therefore our moment diagram is in second order or second degree, then it should have a smiling curvature. Now, for shear diagram that it is decreasing and it is in the first degree or first order, then our moment diagram should be in the second degree or second order, or in quadratic equation, and should be in frowning curvature. Okay? Now, for negative shear, we have our negative shear if we have our shear plot below our reference line, like this one. Now, the same as with the positive shear, if we have our shear that is in zero order, so therefore our moment diagram should be in the first order or first degree, or that is in linear. If our shear is in the first order, therefore our moment is second order. Now take note, if our shear is decreasing, therefore our moment diagram is frowning. Okay, or we have frowning moment diagram. Now if we have our shear diagram is increasing, like this one, we have a smiling moment diagram. Okay, just a quick recap. If we have zero shear, first degree moment diagram. If we have first degree shear, then we have second degree moment diagram. Okay, then if we have decreasing shear, then we have frowning moment diagram. If we have increasing shear, then we have a smiling moment diagram. And these are some of rule of thumbs, no, just to make you familiarize with this relationship. Now let's try to solve problem. And this problem asks us to formulate a shear and moment equation, and using this shear and moment equation, we create or we draw a shear and moment diagram. So we have a beam here that is a simply supported beam, that we have a hinge support and a ruler support at the left and right ends respectively, and we have a uniformly distributed load that is 50 kilonewton per meter in the entire span of the beam, and this span has a length of 4 meters. Okay, so the first thing we do here is to compute for the external reactions. And we know that at the hinge support, we have two reactions. We have horizontal reactions and we also have vertical reactions. But since we know that we do not have horizontal forces in the beam, so we could say that our horizontal reaction at A is equal to 0. Okay, so we could have vertical reaction at A here, that is, let's say that is R A. And then at roller support at B, we could also have one vertical reaction, that is, let's say that's RB. So let's compute the external forces. That is, we have we can sum up moment first at B, that is summation of moment at B is equal to 0, and all the force that is acting counterclockwise or rotates counterclockwise, and that is considered as positive. So we have here RA. Now the moment arm is 4 meters, that's the distance from B to A, and then since RA rotates clockwise, then we have negative rotation. Now our uniformly distributed load here is represented by a resultant force, okay, and that resultant force is acting at the midspan of its length of action. Okay, since our 50 kilonewton per meter is acting on the entire 4 meter length, so therefore its resultant is located 2 meters from the both supports. Okay, so we have 2 meters from the both supports, so we have here, that's the location of the resultant. Now the magnitude of the resultant, it is just 50 kilonewton per meter, then times the length of action, that is 4 meters. Then we can cancel out meters, then we could have the answer that is 200, and the unit is in kilonewton. Okay, so we have the resultant force that is positive, okay, since our resultant force 200 kilonewton rotates counterclockwise with respect to B, so we have 200 here, times the moment arm, that is 2 meters, that is the distance from B, and this equals to 0. And we have RA here, the value of our reaction at A, that is equals to 100. And the unit is in kilonewton, since we know that this 200 here, that is in kilonewton, and 2 is in meter, and 4 here is in meters. So by further simplifying it, so we can cancel out meters, so the remaining would be kilonewton. Now for reaction at B, we sum up force is vertical is equal to 0, then all the force acting upward is positive, then we could have RA, that is positive, plus RB, that's positive as well, minus the resultant of the uniformly distributed load, is 200, and is equal to 0. So since we have computed already the value of RA, then we substitute it here, that is 100 plus RB minus 200 is equal to 0. So we have RB here, that is equal to 100 kilonewton. So they have the same value of reaction, since we know that our beam is symmetrical. Okay, so and then our load is symmetrical as well, so we have the same value of the reactions. So after this, after computing the reactions, we can now proceed in the formulation of the shear and moment equation. So we can create these equations by selecting a cut section in our beam. Okay, but we have to be mindful on the location of our cut section. We have to consider, or we have to look the continuity behavior of our beam. Like in this case, since we know that our beam is continuous from A to B, the meaning of continuous is that we don't have a change in the load. Like in this case, we have a single load from A to B that is only 50 kilonewton per meter. So we could only have one cut section to this one. But in the case of Like this one, we have a uniformly distributed load and we also have a concentrated load P. Now, take note that our P here, our concentrated load P, causes discontinuity in our beam. So therefore, we could have different moment equation for this beam, for this span, and we could also have different moment and shear equation for this span. Okay? So therefore, we should come up with two cross section, or two cut section rather. Going back to our beam, so again, since we only have one single uniformly distributed load all throughout the beam, so therefore, we could cut this with one cross section. Okay, so let's say this is our cross section 1, and our cross section 1 distance varies from our reference point A. So let's say that's x distance from our point A. Okay, so we have our x here that is from 0, okay, to 4. This is valid since again we have continuous beam from 0 to 4 meters. Okay, so we can cut this one, and once we cut this, we could have internal shear, let's say that's our V, and internal moment at any point in our beam. Okay, so let's say that's our shear 1 and moment 1. And then let's try to isolate this segment. So we have the section 1, that is, we have 50 kilonewton per meter uniformly distributed load, the reaction at A, that is 100 kilonewton, and the internal shear and moment at x distance from A is 1. Okay, so our goal here is to create a moment equation and the shear equation. So by using equilibrium equation, so let's determine first shear equation. So we could have our shear equation from 0, okay, to 4. It's the interval from 0 to 4. For shear equation, we just need to sum up forces vertically. That's equal to 0. Upward reaction or upward forces are positive. Then we have 100, okay, that is this force here. Then we have minus the resultant of 50 kilonewton per meter, and this one here is 50 times the length of action, that is x. Okay, that's the length of action. So we have here 50 times x. Then we also have shear, internal shear at the section 1. So we have minus the shear, and this equals to 0. Now our shear here is equal to 100 minus 50x. So this is our shear equation. Now for moment equation, we sum up moment from section 1 is equal to 0, and all the force that rotates counterclockwise are positive. So we have 100. Since the rotation is of 100 is clockwise, so we set that as negative, times the moment arm from section 1, that is x, correct? So we have x. Now the resultant, that is rotating counterclockwise from our 1.1, so we have, so that's positive 50 times x, that is the resultant. But the moment arm, again, that is our resultant, is located mid-span of its length of action, so therefore we have x over 2 distance from our section 1. So we have times x over 2. Then we have the moment at section 1, that is counterclockwise, so therefore that is plus m1 is equal to 0. So again, if we cut our section, this one, so we assume that our shear and moments are positive. So we assume that our shear here is acting downward and our moment is acting counterclockwise. Okay, since this moment or this bending moment here would create a smiling curvature in our beam. So therefore, our moment here is equal to 100x minus 25x squared. So this is now our moment equation. Now, using this shear equation and moment equation, we can now determine or compute the internal shear and moment in any point in our beam. Okay? So we can create our shear and moment diagram by just substituting value of x from this interval 0 to 4. This is valid for this interval again since our beam is continuous from 0 to 4. We do not have a changing load at that interval. Now in our shear and moment diagram, this one is our load diagram, this one is our shear diagram, and the last one is our moment diagram. Okay, in which the vertical axis, that is the value of our shear and our moment, and the horizontal axis, this is the length. Okay, and let's start from the left point, and now we can compute our internal shear at point A by just setting x here is equal to 0, since now our point A here is 0 since that is our reference point. So we can compute the shear, okay, from point A. Then that is, using the shear equation, we could have 100 minus 50x, and then we substitute the value of x, that is 0, so we have 100 minus 50x, or 50 times 0, this gives us 100 kilonewton. Okay, so if we try to plot it at our shear diagram, so at this point we know that this is 100, so we plot it here, that is 100 kilonewton, and our 100 kilonewton shear here is equal to our reaction at A, correct? And then we compute the internal shear at point B, and we know that our point B is 4 meters from A, so therefore our x there is 4. So we have the shear equation, that is 100 minus 50x, so we have 100 minus 50 times 4, this gives us negative 100 kilonewton. So this negative's value here indicates that it is located below the shear diagram. So we have here that is negative 100 kilonewton. Okay? Now, how are we going to plot our shear diagram? So again, take note that our load here is in 0 degree. So therefore, our shear diagram should be in the first degree. So therefore, we know that if we have our first degree line, that is just a linear, okay, or a line that has a constant slope. So we just need to connect these two, and this is now our shear diagram. Now take note, at this point here, we have our shear, internal shear, that is equal to 0, okay? So let's try to prove that one. Now, since our shear diagram is symmetrical, so we could say that the location of our shear is 0 is at 2 meters or at the midspan. Okay? But we can prove that one by using this equation, but by setting as our shear is equal to 0, then we could have, when our shear is equal to 0, what would be the value of our x? Okay? So we could say that we have V1 is equal to 100 minus 50x. So we have our shear is 0 is equal to 100 minus 50x. So therefore, our x there is equal to 2 meters. So the location of our shear is equal to 0. That is when our distance is 2 meters from A. Okay? Since our x refers to the distance from joint A or point A. Okay, so we have now this shear diagram. So let's try to plot our moment diagram. So we have the moment at A here, that is we have moment at A when our x equal to 0. Now using the moment equation, that is 100x minus 25x squared, we could have 100x minus 25x x squared. This gives us 100 times the value of x0 minus 25 times the value of x0, then squared. The result would be 0. So therefore, if we plot our moment diagram at point A, then we have 0 value of internal moment. This is correct since we know when we have a hinged and ruler support, we have our moment that is always equal to 0. We do not have moment at the hinged or ruler support. Unless if it is fixed support, then fixed support, again, we have 3 reactions and that includes moment. Since we know that our shear at this point is equal to 0, that is also the location of our maximum moment. Okay? So the maximum moment occurs when our internal shear is equal to 0. That is where our maximum moment is located. Okay? So how are we going to compute for the maximum moment here? But we know that the x value here at this point is equal to 2. Correct? So we can compute for the moment at x is equal to 2. Okay? So we have, using the moment equation, the moment is equal to 100 x minus 25 x squared, and it gives us 100 times 2 minus 25 times 2 squared, and this gives us 100 kilonewton meter. So therefore, at this point, we have 100 kilonewton meter. Okay? Now, what is the curvature of our moment diagram? Take note, at this side, our shear is in the first degree, correct? This is in the first degree, and it is decreasing. Since it is decreasing, we have a frowning curvature. So we have our curvature like this one. Okay, so this is in quadratic, this is second degree. Now, let's continue our shear diagram, our moment diagram by computing our moment at B. Now, we know that at B, we have our x is equal to 4. So, this one. So, using or computing our moment at x equal to 4, then we have 100 times x minus 25 x squared. We have here 100 times, we have 4 minus 25 times 4 squared. This gives us the value of 0. So again, it is 0 since we are at the roller support. And then the maximum moment here is in 100 kilonewton meter. And our moment diagram here, again, is in frowning curvature since our shear diagram here is decreasing. Okay? And this is in second degree order. This is now our shear diagram, and this one is our moment diagram. Now, let's say if we want to compute the internal shear and internal moment at 1 meter from A, so for example, at this point, if we want to compute the internal shear there, and our internal moment at that point, so we can just use our shear and moment equation by setting the value of x is equal to 1. Okay? So that's the use of shear and moment equation. Now, using this computed moment and shear, then we can now proceed to the computation of stresses. Okay? Which will be discussed in the next videos.